I'm Kihong Kim and CEO of Sendrep. It's a huge honor to be in front of all of you. I would first like to thank Michael and Janet and the executive of CTA. Thank you so much for having me here. What I'm going to tell you about today is a technology called DBP. It's about objective facts that must be accompanied and explanations based on those facts. We use this a lot when working on cyber threat intelligence world. We have automated this technology to a certain level and developed it to greatly assist in related works. And I'm here to share this experience with you because I believe this would eventually lead to a development of technology that would ensure the mutual development of our community. Let me tell you briefly about our company Sendrep first. Sendrep is a cyber threat intelligence company located in South Korea. It's been 19 years since I founded this company, and it has also been listed on the coastal market. We are now providing a public intelligence service called Morales.com, and of course, we are a member of CTA. I majored in computer science at Yonsei University. After that, I founded Sendrep, and I am very interested in malware analysis and CTI technology development. Hyunjong Lee, who will be presenting after my introduction, is conducting research on the application of AI models in the cybersecurity field. Changgyun Kim is conducting research on malware detection using artificial intelligence at KSI R&D team in Korea. Now let's get to the point. CTI specialized companies, especially when a cyber threat occurs, begin the analysis by trying to understand the background like who is the attacker, how did they attack, why are they attacking. After all the threats have occurred, the attacker and attack techniques are analyzed and will be provided in the form of a report. However, this report must be written clearly and based on objective facts. Analysis should not be based on the personal opinions of the particular analyst. So we developed the core technology to figure out how to automate these objective facts. Hyunjong Lee will next present details about the technology.
Thank you, Mr. Kim. I'm Hyunjong Lee from Sendrep. I'm really excited to introduce our research. The order of today's presentation is as follows. First, I will explain the background, and then we will explain the detailed technology and some examples. Starting with the specific reason why I began researching this technology, I'll provide an explanation of DBP. There are 4 key reasons why I start this research. Firstly, the limitation of manual analysis. Secondly, high-level requirement for analysis. Thirdly, the issue of repetitive same threats. And finally, the subjectivity of analysis. Let me tell you more in details. The first reason is the limitation of manual analysis. According to A/B test data, new threats continue to be made every month. The number of threats in February of this year was about 2 million, which is an average of approximately 90,000 threats per day. Due to a limited number of analysts, a lot of new emerging threats cannot be manually analyzed. Clearly, a new approach is needed for covering all these threats. The second reason is a high-level requirement for analysis. Due to many techniques required to analyze threat intelligence, this analysis can only be performed by a small number of high-level cybersecurity experts. The third reason is the repetition of same threats. According to virus total statistics, a significant percentage of the requested data is already known. This means that the same types of threats are repeated over and over again. If the same malware analysis is repeated, the analysis work turns into a simple labor task. In other words, fatigue increases and efficiency decreases. We need a way to identify new highly engineered threats among numerous similar threats. The final reason is the subjectivity of analysis. The results of threat profiling are often said to be determined by analysts' empirical know-how. Therefore, depending on their skills and experience, the results may differ even for the same threat. So we created a technology called DBP, which means Deep Binary Profiler. Its purpose is to automatically analyze the large quantities of threats and generate objective TI information. So what role can DBP play? Below is the representation of DBP's technical tree. Fundamentally, DBP separates malicious code into several functions. Afterward, it discovers whether the function has been reused from past threats. By identifying function reuse, it becomes easier to trace the usage history of the function. This extends the functionality of DBP, allowing it to perform additional tasks. For instance, inheriting the label information from past analysis results, measuring the degree of variation, and distinguishing between new functions and variants. To make these all tasks possible, the similarity between two assembly code must be measurable. However, calculating similarity requires a numerical vector, not just text data, like assembly code. Let's take RGB colors as an example. When working with the color data on your computer, we express the color combination with 3 dimensions, red, green, and blue. Since this is a numerical vector, the similarity can be calculated as you can see on the screen. Like this color data, we need a vector representation methods for assembly codes to compute the similarity between them. To obtain the numerical vectors of these codes, we trained an AI embedding model. This model understands the meaning of assembly codes and converts it into appropriate numerical vectors. I'll not go into detail about the AI part here. If you have any questions about it, please feel free to talk with me individually. The key you should know that is 2 functions with similar code are converted into 2 similar vectors. By calculating similarity between these 2 vectors, it is possible to distinguish whether the 2 functions are the same or different. As a result, we can determine whether it has been reused or not with the function database which contains function data of the past threats. For example, let's say there is a malware that consists of 5 assembly functions. After searching the function from database, the usage history of function is tracked. If the same function has been used in the past, the previous analysis result can be utilized as a reference. The label information from past analysis results, such as T1027, ledger's threat actor, or encryption function of ransomware, can be applied because it's the same function. The DBP analysis results are as shown in the picture. It's largely divided into 2 parts. The first part on the left is the analysis result for each function. It includes the name of functions, identified labels, and hash information for files using the same function. The second part is summary information that aggregate the analysis result for each function. It provides how many functions belong based on label information such as threat actor, threat category, and technique ID. This part is a case study for how DBP can be applied. From here, my coworker Changgyun Kim will continue the presentation. Thank you.
Thank you, Hyunjong, for a nice explanation about the DBP. From now on, I would like to discuss how DBP could be applied in practical scenarios. We conducted an analysis of 2150 data collected on December 19th, 2022. When we see the left side of the graph, the red part, 888 of them are classified as malicious. Our analysis focused on these malicious data employing DBP. When we see the right side, approximately 80%, 699, were identified as variant threats, and 20%, 189, were new threats. In here, when we are saying variant threats, that means the threats that can be correlated in our threat database. New threats are the opposite cases. Through DBP analysis of 699 variant threats, we were able to identify the most commonly used threat categories, TIDs, and threat actor. The blue graph represents the three categories, the green graph represents TIDs, and the red graph represents the threat actors. Going further, we could also analyze reciprocal relationships. Please look at this pie chart. Based on the DBP result, you can determine which threat actor is carrying out the attack with which threat categories and which TIDs are used. Let's take a closer look with a more specific example. In our database, we have stored functions used in the past by the Lazarus Group's testable malware. By verifying new threats, reusing of these functions, we can analyze whether the function have been partially modified or if it is using the exact same functions. Through this capability, we are able to trace the testable malware used in the 2014 Sony Pictures attack within the collected data. Starting from the discovered testable malware, as a starting point, we tracked the reuse relationships of malicious code functions that exhibited more than 40% variation from the base file. As a result of this tracking, we were able to identify 37 similar threats. So we drew a graph about these 37 threats. The nodes are indicating the 37 threats, and the number on the edge indicates the ratio of function reuse. When categorized based on the identified threat actors, we observed the separation into three distinct clusters. The cluster 1 is the Lazarus group, showing the red. The cluster 2 is the APT17 group, showing orange. The cluster 3 positions between cluster 1 and cluster 2 is another smaller APT17 group, marked in orange as well. You can see that cluster 3 are reusing functions from other two clusters. Which group originally implemented these functions? Let's arrange the nodes in this graph based on first seen date and number of functions. Here are the arranging results. Analyzing the graph, we can see that in 2022, another new APT17's attack emerged by reusing functions from APT17 and the Lazarus group. DBP can provide digital evidence as well. These assembly codes serves as digital evidence for function reuse. The functions you can see here are used in cluster 1 and cluster 3. As you can see in the assembly code, even though the screen is pretty small, they're using the same function. By analyzing the user's history of the function on the left, it becomes evident that it is a function frequently employed by the Lazarus group. These functions are used in cluster 2 and cluster 3. When you see in the assembly code as well, the same functions was used. Looking at the graph on the left, we can see a history of the uses by the APT17, Lazarus, and Petrarch groups. However, it is evident that these functions are overwhelmingly used by the APT17. Additionally, this function is associated with the T1082, but when we check the user's history of this function, there is no information about the third actor. This indicates that it is a function which the third actor has not been founded by DBP. We will now proceed to summarize the DBP research. There were a total of 4 problems, and we were able to alleviate these problems with DBP. First of all, limitation of manual analysis. With DBP, we can automatically analyze threat intelligence and significantly reducing analysis time. Next, demands of high-level analysis requirements. Okay, start again. Next advertisement. We are using MacBook as well. DBP can utilize information from past analysis of the same functions to provide precise direction. Third, repetition of variant threats. Normally, when we try to collect data, more than 60% were variant threats. DBP can distinguish whether a threat file is newer variant, helping to pinpoint the starting point for analysis. Finally, there is a subjectivity of analysis. Depends on the expert's personal experience, the analysis result could be different. Through DBP, it is possible to provide objective evidence for analysis result in assembly code. Thank you. Mr. Kim will conclude the presentation.
Thank you to our 2 researchers for their hard work. Our technology which we introduced is not a technology that replaces existing technologies, but is designed to be used together with existing technology to access the root cause of attacks and to share objective facts to enable more effective responses. Of course, you will be able to explain not only the attack, but also who did the attack and what attack techniques was used. Backdata and automated technologies based on objective facts, which we looked at earlier, eliminate redundant analysis issues from various communities active in the cyber threat intelligence world. In other words, it reduces the complexity because even a single attack can be interpreted in various ways. Cyber threats are continuously increasing. In addition, it will become more advanced and faster with generative AI technology. However, human resources and analyst capabilities have physical limitation. Like our technology, the underlying technology that will be used for intelligence will maximize the efficiency of the human resource itself and increase its ability to respond per unit of time. I think that this is the true community effect that we said we are pursuing. Thank you for listening. We will have a short Q&A session from now on.